Let's start relations on the set A and different types of relations on set A. So relation on set A means that R is from R A to A. R is from A to A. Means that let's say if A is 1, 2, 3, 1, 2, 3. Let's say this is your set A, and relation on set A means that how an element of the same set is related to other elements, how any element of a set is related to other elements of the set. First of all, if I just give it a graph, means the vertices of the graph associated with any relation R is going to be, it will have nodes like 1, 2 and 3, 1, 2 and 3. Now let's say if 1 is related to 2, then you will have a directed edge from 1 to 2. Okay, if 1 is related to itself, then you will have a directed edge from 1 to itself. Let's say 3 is related to 2, then you will have a directed edge from 3 to 2, and 3 is also related to 1, then you will have a directed edge from 3 to 1. Let's say 2 is related to itself, then you will have a self loop kind of thing on 2. So from this graph you can say what is the relation. So relation is 1 comma 1 because of this edge, or you can say this because of this self loop, and then because of this directed edge you can say that another ordered pair of this relation is going to be 1 comma 2. So an edge means that 1 is related to 2. This edge means what? This means that 1 is related to 2. What does this edge mean? This means that 1 is related to 1. This edge means 2 is related to 2. This edge means 3 is related to 2. This edge means 3 is related to 1, right? So 1 comma 2, 1 comma 1, 2 comma 2, 3 comma 1, and 3 comma 2. So this is your relation R. So relation is a set of ordered pairs, and here it is the relations on the same set. Okay, we are talking about relations on same set. Relations on same set, right? Basically, for any relation on same set, in your graph, what are the vertices? Vertices are the elements of A. So elements of A means in a graph representation of a relation on same set, in a graph representation of a relation on set A, vertices is equal to elements of A, or simply vertices is equal to the set A. Set A is the vertices, is a vertex set, and the edge is equal to relation, right? Now let's look at different types of relations on set A. So if this is my set A, then for any relation, the vertex set, the graph associated with that relation, the vertex will be the elements of A. So this is one vertex, right? Now, one type of relation on set A, one type of relation is called reflexive relation. What is reflexive relation? If every element is related to itself. So reflexive relation on set A. So a relation R, a relation R on a set A is reflexive if every element is related to itself. Every element is related to itself. Means that for all A that is an element of A, for all A belonging to A is related to A. So a reflexive relation, the minimum number of elements in a reflexive relation. So if I have to write a relation and it is known that this relation R is reflexive, then I know for sure that these elements have to be related. Means I know for sure that 1 comma 1, 2 comma 2, 3 comma 3 has to be, these ordered pairs has to be in that relation. Okay, and the other edges, like from 1 to 2, from 2 to 3, or from 2 to 1, or from 3 to 2, the other edges, when it comes to any two distinct vertices, they may be connected, they may not be connected. That does not uh, their presence or their absence does not disqualify a relation to be reflexive. Means their presence or their absence we're not looking at. If we have to check whether a relation is reflexive or not, we just have to see that if every element is related to itself or not. So there may be other elements, but while checking if the relation is reflexive or not, we are not looking at that. We just have to make sure that if the elements are related to itself or not. Maybe some other. So this is the smallest reflexive relation. This is the smallest reflexive relation. Let's say R1. R1 is the smallest reflexive relation. So smallest reflexive relation. But any other relation can be reflexive. Let's say R2 is also reflexive if there are other elements, if there are other ordered pairs there. Apart from these three, there may be other ordered pairs possible. So R2 is also a reflexive relation, and likewise any other. So what is the largest reflexive relation? A cross A, because A cross A is also, it's like when it comes to, we know that A cross A is a universal set in the context of relation. So in this case, in the context of relation on same set, so in this case the largest reflexive relation is A cross A. Largest reflexive relation is A cross A. There are other aspects about any relation that any special type of relation that we will talk about, like reflexive relation is one of them. Maybe symmetric relation, anti-symmetric, asymmetric, transitive. These type of relations we will see in this video, maybe all of them. But there one more aspect of it, like how many different transitive relationships or how many different reflexive relations possible. Means for a given set A, how many different reflexive relation you can make. Similarly, for a given set A, how many different symmetric relations that is possible. For this type of, I can do it right now also, but I am just keeping it to for later, after combinatorics. Okay, in the discrete mathematics itself, in this playlist, I will start combinatorics, and and at that time I will just randomly, as a combinatorics topic itself, I will look at the number of reflexive relations possible, number of symmetric relations possible, and that's it. Because that will be in the right flow. Okay, so let's look at another type of relation on set A, which is symmetric relation. So let's look at another type, not only symmetric. Let's see symmetric, anti-symmetric, and asymmetric at one go. Means at the same time, let's look at what these type of relationships are. Okay, let's say what is symmetric relation. Symmetric relation is like for any two distinct element, for any two distinct element of the set, if there is a relationship, means let's say if 1 is related to 2, or 2 is related to 1, or let's say 3 is related to 2, if there is a relationship between two distinct elements, then it has to be both ways, then it will be called symmetric. So you can think of it this way. For example, if I take a real life example, then let's say you have a let's say you have a um, set of set of people who belong to the extended family. Okay, and then you will say that one element is related to another element if they are cousins. So A is related to B if A is a cousin of B. Now in the relation, if A is cousin of B, then B is cousin of A. So that type of relationship is called symmetric relationship. That if for two distinct elements there is a relationship, it goes both ways. Then it is called such a relationship on same set. Such a relationship on a set is called a symmetric relationship. If the elements of set are related in such a way that for two different elements the relationship holds both ways, then it's a symmetric relationship. Now, the anti-symmetric relationship is that if there is a relationship between two distinct elements, then it cannot be both ways. If there is either there is no relationship, or if there is relationship, then it has to be from one side only. Like only A has to be related to B. If A is related to B, A is not equal to B. If A is related to B, then B does not is not related to A. So, what type of real life example I can take for antisymmetric is that, yeah, let's say it's a family, means a extended family. On take the case of extended family, set of extended family members. Then let's say the relation R is younger. Relation R is younger. So if A is younger than B, then A is related to B. So clearly, if A is, let's say, 24 years old and B is 30, then A related to B, but B is not related to A. For sure, B is not related to A. Okay, so this is about antisymmetric. And what is asymmetric? Asymmetric in okay, for symmetric or antisymmetric, uh, the relate the any element may be related to itself or may not be related to itself. Means this type of relationship, like 1 comma 1, they do not have a say in determining whether the relationship is symmetric or antisymmetric. If any such ordered pair exists or does not exist, it does not have a say whether the relation will be symmetric or antisymmetric. Means an element related to itself does not have a say. Now, but if you think about it, in symmetric, what is in symmetric relationship, what we actually doing is this, that A comma B is an ordered pair, then B comma A is also an ordered pair. So we are switching the places. In an ordered pair, the first element and second element, their order is important, right? Now, in a symmetric relationship, what a symmetric relationship demands is that if if such an element exists as if such an ordered pair exists, then this ordered pair must also exist. Now, if you think about a relationship, if you think about an ordered pair like this, that is A comma A, now you can say that, okay, I am changing the position, and then again A comma A. So it's kind of symmetric. It's kind of symmetric. So anti-symmetric, let go of this. Anti-symmetric in anti-symmetric relationship, this is ignored. This sort of this sort of symmetricity, you can say. This is kind of symmetric, but in anti-symmetric it is ignored. But in a asymmetric, how asymmetric is different is that in asymmetric it is also ensured that such type of symmetricity is also not there. Okay, so I will just define three types, and you will understand. I mean, you have understand because I am a fantastic explainer. So what is symmetric? Symmetric means that a comma b belongs to R, then b comma a belongs to R for a not equal to b. For all a and b belonging to R, a not equal to b, then okay, this is symmetric. And what is anti-symmetric? Anti-symmetric is then a is equal to b. This is anti-symmetric. And what is asymmetric? Asymmetric is that a comma a, any a comma a does not belongs to R. There cannot be any one ordered pair, that is means there cannot be a case where any one element is related to itself. Or a not equal to b, then a comma b belongs to R. For a not equal to b, if a comma b belongs to R, then b comma a does not belongs to R. So this condition holds for anti-symmetric also, that for a not equal to b, if a comma b belongs to R, then b comma a does not belongs to R. So as you can see, for symmetric and anti-symmetric, this sort of relationship, that any element is related to itself, this sort of relationship, whether it is there or whether it is not there, it is not going to it is not a deciding factor for us. We don't even care to look at such a relationship is there or not. It may be there, it may not be there. But asymmetric, it does not have to be there. If that is the case, then it is not asymmetric relationship. So if, let's say, let me try to draw asymmetric relationship from this is a given, this is three vertices given. Let me try and have a symmetric relation. So what is the minimum without adding any edge? Without adding any edge, it is symmetric. Because if you don't, because if there is a relation, okay, there's no edge from between any two distinct elements. I don't have to check for whether b comma a is there or not. So the smallest symmetric relation is phi. The smallest symmetric relation is phi. What about anti-symmetric? Again, in anti-symmetric also, the smallest is phi, because there is no edge between any two distinct elements. I don't have to check for the condition. If I don't have to check if the condition is being violated or not, there is no edge in the first place. So for symmetric and anti-symmetric, then for smallest symmetric or for smallest anti-symmetric, this is phi. What about asymmetric? It is also phi. So smallest symmetric, anti-symmetric or asymmetric, it is phi. Smallest asymmetric or symmetric or anti-symmetric. Smallest such phi is the smallest. Now, what about largest? What about largest? So largest symmetric is A cross A. That's for sure. Largest symmetric. Largest symmetric relation is A cross A. Okay. Let's try to okay some results regarding the graph of a symmetric relation. Okay, graph of a symmetric relation. If you see, there can be self loop. Can there be self loop? Yes. There may be self loop, there may not be self loop based on whether an element is related to itself or not. But if there is an edge between two distinct elements, let's say from 1 to 2 there is an edge, then 1 is related to 2, then 2 must also be related to 1. So you can see there is a back and forth edges. So what we replace it with? We replace it with bidirectional edge. Means that we do it something like this. This is how we represent a symmetric edge, symmetric graph. So for a symmetric relation, the graph of the symmetric relation. So graph of symmetric relation. Okay, I am erasing this part. Graph of symmetric relation. There can be self loop if if any element is related to itself. If any element is related to itself. Self loop if any element is related to itself. And bidirectional edge if in case any two distinct elements are related to each other. In case any two distinct elements are related to each other. So this is every symmetric relation. For every symmetric relation, the corresponding graph would have two types of edges only, either self loop or bidirectional or both. So combination of them. What about anti-symmetric? So now I will change it. Graph of anti-symmetric relation. Graph of anti-symmetric relation. Self loop if any element is related to itself. And unidirectional. Unidirectional edge in case an element is related to some other element. Means two distinct elements cannot be related to each other in anti-symmetry. So unidirectional edge in case any element is related to any other element. Okay. So let's say I take an example of a any example of anti-symmetric. If one is related to two, it will be like this. And now there will not be an edge from 2 to 1. Let's say 2 is related to 3. Let's say 3 is related to 1. So what is this relation? Let's say this relation is R3. Let's say this relation is R2. Then R2 is what? R2 is 1 comma 1, 1 comma 2. Now 1 comma 1 is allowed. 1 comma 2, if you are doing this relation, if you are means if this is an ordered pair, then 1 comma 2, then 2 comma 1 cannot be in this relation. Similarly 2 comma 3. So if 2 comma 3 ordered pair is in the relation R2, then in R2 3 comma 2 cannot be there. 3 comma 1. If 3 comma 1 is an element of R2, then 1 comma 3 cannot be an element of R2, given R2 is an anti-symmetric relation. Okay. Now let's look at asymmetric relation. In asymmetric relation, there cannot be any mm, element that is related to itself. So this part cannot be there, self loop, because no element is related to each other. No element can be related to itself, so no self loop. And if there is a relation from between two distinct elements, it has to be one way. So either 1 comma 2 or 2 comma 1, either 2 comma 3 or 3 comma 2. Let's say this is it. So what type of relationship is this? Means if this is R3, then what is R3? R3 is 1 comma 2, 3 comma 2. So unidirectional edge in case any element is related to any other element, to another element. This is graph of asymmetric relation. So you can see in asymmetric relation there is no self loop, there is no bidirectional, there is only unidirectional edge. So if I have to summarize, then in symmetric you can have self loop. You can have you means you may not have. This means of course you may not have. You may have. This means allowed. If there is self loop, yes, it's okay, no problem with that. Uh, Self loop and bidirectional. Self loop and bidirectional. Can there be any unidirectional edge? No. In asymmetric, no unidirectional. No unidirectional edge. What about anti-symmetric? Can there be self loop? Means self loop is allowed. Yes. No bidirectional. No bidirectional. And then unidirectional. It's okay. What about symmetric? Only unidirectional. Only unidirectional. No self loops. No bidirectional. Okay. Now there is another type of relationship which is a transitive relationship that we will see in the next video. Thank you very much.